Well, good afternoon, everyone. Welcome. Hope your week is going well so far. We've certainly had some beautiful weather here in Santa Barbara. And for those of you that are here in Santa Barbara, I know you're probably all enjoying that. So anyway, you have your first exam under your belt now. And the exam went very well. A lot of you did very, very well on the exam. So anyway, I appreciate your hard work in this class, and I appreciate the performance on that first exam. I encourage you all to keep it up, because I'm watching your work on mastering, and I see that you're doing it consistently, and you're staying up with the class, and I think it really paid off on the first exam. So keep that up, and we'll keep moving forward. The first exam, covers a lot of stuff that you've seen before, probably. So it might get a little bit harder from here on forward as we start looking at things that you haven't covered so much. So just keep that in mind, and know that if you keep up, you can continue to excel on those exams, okay? All right, before I get started today, just a couple of quick announcements. First of all, now that we've been through, sort of 3 weeks of classes on Zoom and our first exam, I'm kind of evaluating how it's going, right? And I'd love to hear from you. You are the reason I'm here, and I want to make this experience a good one for you, and I wanted to make it one in which you're learning chemistry, right? Because even though we're learning this way, my responsibility to you is to teach you the material that you need for this course for the future, right? You may want to go to med school, you may want to go to grad school, you may need this material in other courses, and my responsibility to you is to make sure you're learning it, right? So I would love to have some feedback and on what you think is working and not working so far. So probably the best way to do that is to send me an email. So please email me with any comments you might have, any criticisms, any suggestions. How is this going, right? Basically, I want to know how it's going for you. And so for those of you that have a little bit extra time and can send me a quick email, just letting me know how it's going for you, the entire experience, and if there's any suggestions, I would really appreciate it. Because for all of us, this is, well, at least for me, it's the first time teaching an entire course online. I've been teaching chemistry for 30 years, but never like this, right? So I want to do my best, and I want to do my best for you. I welcome feedback. Okay. All right. Before we get started, are there any questions on anything? Use the raise hand function if you have a question. And thanks to those of you that have your cameras on. I love to just be able to see you. It just makes this whole experience so much better. So I really appreciate that. Questions? No questions? Okay. I don't see any questions. So great. We'll go ahead and get started then. You can always ask questions during the lecture. Just use the raise hand function. And let's see. Okay, can you see my screen? Can you hear me? Awesome. Great. All right, we will get started. Okay, so we're gonna jump, change gears a little bit here and keep going along the same kind of path we were on. So if you remember, we sort of started out with some fundamentals, right? Units, conversions, things like that. And then we jumped into atoms and elements, right? So we learned about atoms and elements. We learned how they were discovered, right? And why that discovery was so important, right? The particulate nature of matter, and the idea that the properties of matter depends on the structure of those particles, right? The unifying theme of all of chemistry is that the properties of matter depend on the structure of these particles that compose matter, right? And so we learned about the discovery of atoms. We learned how to do things like convert from grams to moles. We learned a little bit about the periodic table, right? And then we jumped into molecules, right? And we started to see how atoms can bond together to form molecules. We learned a little bit about molecules. We learned how to name them, for example, right? We learned how to look at their chemical composition, right? And how to calculate things like percent by mass. And we learned how to get their formulas from experimental data, right? So that's where we've come so far. And now we're just going to take the next step and start looking at chemical reactions, all right? So all of you are probably pretty familiar with chemical reactions. You've seen them before, right? I'm going to often abbreviate reaction like this. But basically, a chemical reaction is a process by which atoms and elements combine and rearrange to form new substances, right? And we've already seen some examples of that, for example, like combustion, right? So that's where we're heading. I love this quote by Linus Pauling. Linus Pauling was a Nobel Prize winning chemist. He developed some of the early theories of chemical bonding. And actually, when I was a graduate student at Stanford, I got the opportunity to hear him give a talk. And he was probably, I don't know, late 80s, early 90s, probably late 80s. Anyway, he gave a really nice just chalk talk. He went up to the board and wrote things down, and in his own charming way, right, told us a little bit about the research he was doing. But anyway, he said, I feel sorry for people who don't know anything about chemistry. They are missing an important source of happiness. Right? You don't often hear chemistry and happiness together in the same sentence, but to me, this is true, right? Because it gives us a real understanding of the world around us and the amazing connection between the things that we can see and their properties and this world that lies underneath, right, that we can't see, and that we can actually make that connection and understand it is pretty amazing. All right, so let me introduce a little bit about particularly a topic called stoichiometry, which will be a topic of this chapter. So we'll start talking a little bit about climate change. You guys have probably all heard of climate change already many, many times, right? The idea is that there's this natural effect on our planet called the greenhouse effect. Our atmosphere kind of acts like glass does on a greenhouse. And you know that if you go in a greenhouse, even if it's not very warm outside, it'll be warm in the greenhouse, right? Similar thing happens in your car, right? Even though it's not very warm outside and your car is locked up and you have windows, it's warm in your car, right? If it's closed up. Why is that? Because the atmosphere, just like glass in a greenhouse, allows energy of the sun to go through as visible light. We'll be talking more about light a little later in this course, but it allows the energy of light to come through, right? And then that light gets converted to thermal energy, right? It gets converted to thermal energy as it hits things on our planet, right? And then our planet re-emits that energy as infrared light, as light of much longer wavelength, okay? So infrared light goes out, but there are certain gases in our atmosphere called greenhouse gases that absorb some of that infrared light going out, right? So in other words, these gases kind of act like glass does in a car or in a greenhouse. They allow visible light in, but they don't allow the infrared light out. This is the same thing that happens in your car, right? So that's why your car is warmer, right, than its surroundings when you park it out in the parking lot in the sun, right? Visible light comes in through the windows, heats up the interior of the car, but that heat can't escape because the windows absorb that infrared light, which is basically a way that heat can give off energy, right? So So that energy gets trapped inside. Now, this is a natural effect, right? If these weren't here, right, if the greenhouse gases weren't here, our planet would be a lot cooler, right? In fact, you know, we'd probably be skiing down off La Cumbre Peak, right? If this greenhouse gases weren't here, right? So it's a very important part of our atmosphere, of course. The problem is that the amount of greenhouse gases is increasing, right? And it's increasing. One of the most important greenhouse gases is carbon dioxide. And if we measure the amount of carbon dioxide, if we follow it as a function of time here, we can measure it in the atmosphere pretty accurately, right? This is from about 1860, a little before 1860. And you can see that the increase. Now, notice this graph is not zero, right? This graph starts at 290, so this exaggerates the effect, right? But you can clearly see, right, that greenhouse gases. Atmospheric carbon dioxide has increased, right? It's gone from about 290 parts per million up to exceeding 400 parts per million, and it goes up by about 0.5% every year, right? So since CO2 is one of the big greenhouse gases, we kind of expect the greenhouse effect, right, to be amplified by that, right? Because if you're basically trapping the CO2 is a gas that, again, allows the visible light in, but traps the infrared light. And if you add more CO2 to the atmosphere, right, you're going to trap more of the infrared light, yeah? And so this natural balance, which keeps the Earth at a particular temperature on average, is changed to some degree, right? So we can see the effect here in average global temperature, right? So we've been keeping track of average global temperature for a while. And you can see that it fluctuates quite a bit, right? You can't really say anything about global warming based on data from one day or 1 year even, right? You really have to look over a long period of time, right? Because our temperature of our planet, our average temperature fluctuates for a number of reasons, for many, many reasons, right? But you can see the general trend here, especially since about the 1950s, right? When we really started adding a lot of greenhouse gases to the atmosphere, is that global temperatures have risen, right? And this is degrees Celsius, so we're up about a little over 1 degree Celsius here. On average over this time period. All right, so why am I going into all this? I'm going into all this because there are, you may have heard some claim, one of the things that I really hope you take away from this class is to become an educated citizen as well as understanding chemistry. And understanding science and chemistry is part of being an educated citizen. And a wise contributor to society, right? That's what I hope for all of you. And what I've heard, like sometimes I was listening. There's one time I was listening to this talk show on the radio while I was driving, and the person speaking was saying how, oh, we don't have to worry about carbon dioxide from fossil fuel combustion. Why? Because volcanoes emit more carbon dioxide than fossil fuel combustion does. And I thought, oh, interesting. Is that true, right? Well, it turns out deciding whether or not that's true is a matter of doing a problem in stoichiometry, right? Which is the topic of this chapter, right? So this is the equation by which, the chemical equation by which hydrocarbons like octane, this is octane, the component of gasoline, burn in air to form carbon dioxide and water, right? And notice this is the culprit, the carbon dioxide here. If you're burning a lot of octane, if you're burning a lot of hydrocarbons, right, fossil fuels, then you're producing a lot of CO2, right? And we see that increase. So the question then becomes, okay, was this person right? Was this person right when they said that volcanoes emit more carbon dioxide than fossil fuel combustion? Well, what do we need to know? We need to know how much octane is burned, what amount of hydrocarbons are burned. And from that, we can figure out how much carbon dioxide is emitted into the atmosphere, right? From this equation, we know that for every 2 molecules of octane, we get 16 molecules of CO2, right? Or for every 2 moles of octane, we get 16 moles of CO2, right? This equation gives us the relationship, right, between the amount of octane and the amount of CO2, okay? So that idea is called stoichiometry. So the relationship between the amounts of reactants and products in a chemical reaction, right? The relationship between the amount of reactants and products in a chemical reaction. That's called stoichiometry. So stoichiometry, you know, basically the stoichiometry that you learn in this class will allow you to answer this question about whether or not hydrocarbons produce more carbon dioxide or volcanoes produce more carbon dioxide. Because geologists have measured the amount of carbon dioxide produced by volcanoes, right? We know how much hydrocarbons are burned by the world, right? So we can take that amount of hydrocarbons and we can figure out how much CO2 is emitted, and then we can compare the numbers. Yeah, does that make sense? So that's what we're kind of setting out to do here. Okay, let me stop and see if there are any questions. Any questions? You guys are quiet today. Okay, all right, so before we get to that question, we got to cover a couple of things. First of all, we got to understand about a balanced chemical equation. And now you already saw a video on that before class, right? On how to balance equations. So I'll go over the process really quick, and then we'll just do a couple of examples. And then we'll talk about reaction stoichiometry, and then we'll come back and do this calculation and see how much CO2 is produced and compare that to how much is made by volcanoes, okay? So in a chemical equation, we'll often specify the states of the reactants and products, right? With these abbreviations, G for gas, L for liquid, S for solid, and AQ for aqueous, okay? So keep in mind that that's what that means when you see that next to the reactants and products in a chemical equation, all right? Here is the process that you can use step by step to balance a chemical equation, right? You write the skeletal equation first, then you balance the atoms that occur in most complex substances first, and always save elements for last, right? You save the free elements for last, because when you balance those, you don't mess up everything else, right? Because they're free elements. And then you clear coefficient fractions, and then you can check that by summing the sides of atoms on both sides. They have to be the same, okay? We can't create or destroy matter when we write a chemical equation. All the atoms have to be accounted for. So let's just, again, since you've already seen a video on this, let's just do a couple of examples, and I'll have you do one just to make sure we got this, okay? So in order to do this example here, we got to remember a little bit about nomenclature, right? Which we just did on the exam. And again, most of you did very well on that part, so good job. So I'm guessing you can all do this as well. So I want to write a balanced equation for the reaction of solid cobalt-3 oxide and solid carbon to produce solid cobalt and carbon dioxide gas. So the first step here is to write a skeletal equation by writing the formulas for each reactant and product. A skeletal equation is just an equation that's not balanced, okay? So let's do that first. So it's going to be cobalt-3 oxide. So if it's cobalt and oxygen and it's cobalt-3, right? The charge of oxygen is 2 minus. So the way to make this charge neutral is to have how many cobalts?
2.
Cobalt 2, CO2, and then how many oxygens?
3.
3, correct, right? So that's cobalt-3 oxide, right? The 3 oxygens are -6, the 2 cobalts are +6, right? So it's neutral. All right, and then it says it's solid, so we're gonna write the little solid next to it, right? And then it says plus, it reacts with solid carbon. So we're going to just write the element carbon, right? And it's going to produce solid cobalt, right? And carbon dioxide gas, right? So there's our balance, that's our skeletal equation, all right? Now the second step is to balance, where did my other pen go? The next step is to balance substances that occur in, balance atoms that occur in more complex substances first. So when you look at this equation, right, these are elements, okay? So pure elements like that, save for the very end, because you can balance them without messing up everything else, right? So save those for the end. Let me see something here. Okay. We'll save those for the end, and we'll balance the more complex things first. So let's start with the CO2O3, right? We have 2 COs here, right? So we're going to put a 2 right here, right? And then we got 3 oxygens, right? So we're going to put a, let's see, sorry. Look at my example here real quick. 3. Yeah, because you put, you have 3 oxygens, right? So you need 3 halves CO2, right? Because that's going to give you your 3 oxygens, right? And then that gives you 3 halves carbon over here, right? So let's see, is that balanced? 2 cobalts, 2 cobalts, 3 oxygens, 3 oxygens, 3 halves carbon, 3 halves carbon. Yeah, that works, except that it doesn't have, let's see what I do wrong here. Oh, it has fractional coefficients in there, so we got to multiply by 2 to clear them all, right? So when we multiply by 2, we get 2 CO2O3, and then this goes away, and then this becomes 4, right? And then this goes away and becomes 3. 2, 3, 4, 3. That's correct. Okay. That's this last step right here, number 4. Okay. Does that make sense? All right, awesome. All right, let's try another one. Acetic acid. So HC2H3O2, and that's going to be aqueous. Reacts with the metal aluminum plus aluminum solid to make aqueous aluminum acetate. So that's, we got to write the right formula for that. Notice that when you write these things out, you got to get the formulas for each compound correct. C2H3O2. All right, and that's a -1 charge. Aluminum is +3. So how many acetates do we need?
3.
3. Correct. Okay, so that is the skeletal equation. Okay, I see a question. Jane.
I just was wondering how we know which to start with, because I was getting confused on that in the practice question.
Okay, so you always want to leave pure elements for last. So never start on a pure element, right? Always start on a compound. And so it's like, for example, on this one, as you're going across, you'd want to start with this over this because that's a pure element, right? So you can start with that one and you say, aha, 2 COs. So you put in the 2 there and then so on, right? Now, sometimes it takes a little bit of guessing and a little bit of back and forth, but eventually if you play around with it, you can get it, right? But these are just guidelines. Do the more complex things first and then save the pure elements for last. That should go a long way towards helping you do it in the right order. Does that make sense? Jane? Okay.
Yeah, that makes sense.
All right, awesome. So then, okay, so let's continue on this one. Acetic acid reacts with aluminum metal to make aqueous aluminum acetate plus hydrogen gas, right? So now this contains, notice that this contains a polyatomic ion, all right? When you see polyatomic ions in a chemical equation, balance those as a unit, right? Especially if you see them on both sides like this, balance those as a unit, right? It'll save you a lot of trouble rather than trying to balance the individual atoms of each component of the polyatomic ion, okay? So balance that as a unit, okay? So we'll look here, and so what do you think we should start with? So I see your question, Danielle.
Hi, I'm just wondering how you got the subscript for the product with aluminum and the acetic acid.
Right here?
Yeah.
Yeah, so I know that aluminum is 3+, right? Because of its position in the periodic table. And I know that acetate is C2H3O2 minus, right? So in order to make this a neutral compound, I need 3 of these, so I have a 3 minus and 3 plus charge.
Okay, thank you.
Yeah, you're welcome. Okay, so what do you think? What should I balance first? Acetic acid or aluminum?
Acetic acid.
Acetic acid, yes, right? So I know, so I'll look here, I see this acetate, I'm gonna balance as a whole. I got 3 acetates here, so I'm gonna put a 3 in front of that, right? Okay. And then now the next thing, now notice that I have 2 different hydrogens here, which is a little bit confusing, right? Because I have this hydrogen and this hydrogen in here. But remember, I'm balancing this as a unit, right? So I'm gonna balance that hydrogen separately from that hydrogen, right? Because the hydrogens that are in here are gonna get balanced with this 3, right? So I have 3 acetates here, 3 acetates here, right? So that balances that hydrogen, but this hydrogen is not balanced, correct? So how can I balance that hydrogen?
You would need to get it to a multiple of 2. So it's because it's H2 on the other side.
Exactly right. So it'd be 3 halves H2, like that, right? Because 3 halves of H2 gives me 3 hydrogens, yeah? Okay. Now I can go ahead and balance the aluminum. I have 1 aluminum here and I have 1 aluminum there, so that's already balanced, yeah? So now the last thing is this step 4, if the balance equation contains fractions, clear these by multiplying the entire equation by some integer that clears them, right? So in this case, again, it's gonna be times 2, right? So this is gonna become 6, this is gonna become 2, this is gonna become 2, and this is gonna become 3. Right, so the balance equation is 6 acetic acid plus 2 aluminum goes to 2 aluminum acetate plus 3 H2. Does that make sense? All right, let's do one more example and then I'll have you do one. All right, so this one is to write the balance equation to show the reaction of gaseous ethane. So C2H6, oops. C2H6 gas plus oxygen, right? Gas to form carbon monoxide gas plus water vapor. So the vapor tells you that that's a gas as well, right? So there's my skeletal equation. Let's go back to the procedure here. Balance atoms that occur in more complex substances first. So what should I balance first here? C2, oh, this would be C2H, sorry, C2H6, right? Yeah. All right, so what should I balance first?
C2H6.
Yeah, I could start with that. I also have water on this side. I could start with that, right? I could start with carbon monoxide. I could start with any of these things, right? But I wouldn't want to, by any means, start with O2, correct? All right, so let's start with C2H6. So we got 2 carbons. So what am I going to put? 2 here to balance that, right? And then I have how many hydrogens?
6.
6, right? So I'm going to put, so I have H2 over here. So what should I put?
3.
3, correct. Let's see. Emily, do you have a question?
Yeah, just a quick question.
Yeah.
So when we see oxygen in, it's not on the screen right now, but the problem, should we always assume that that's going to be O2?
Oh, great question. Yeah. So remember, that's one of those diatomic elements that we learned about in the previous chapter, right? And so yes, O2, oxygen's always O2, hydrogen's always H2, the halogens, chlorine, bromine, iodine, and so on are always Cl2 or Br2, right? So we need to write those as those diatomic elements. That's good. Good point. Yep. Hey, Yun? Hey, Yoon, did you have a question? How about Emmanuel? Emmanuel, do you have a question?
Not a question, just a quick comment. Also, just remember too, when you're calculating these too, like when you're changing them, you have to do it like, if it's any of the diatomics, you have to do it ×2.
Correct.
Just so
Yep.
everyone knows.
Because the number of atoms is always going to be the coefficient times the subscript, right? In other words, if I have 3 H2O molecules, how many H atoms do I have? 6.
Oh, 6 right there, yeah.
Right?
No, I know. I just meant like, you know, when you get like the mass of it.
Oh,
like in
yes.
some calculations, you have to do it twice.
Correct.
It's not just one element.
Correct.
Of
Correct.
oxygen.
Yep. When you have it in its pure elemental form, absolutely.
Yeah.
Okay. Very, very good. So, so we balance the carbons, we balance the hydrogens. What's left to balance? The pure element oxygen, right? So if you look over here, I got 3 oxygens plus 2 is how many? 5. So I need 5 on this side, so I'll have 5 halves here, right, to give me 5. And again, I have this 2, so I'm going to multiply the whole thing times 2, right? That gives me 2. And then this becomes 5. This becomes 4, right? And this becomes 6, right? So it's 2C2H6 plus 5O2 plus 4CO, goes to 4CO plus 6H2O. By the way, you can always check these, right? You should never get one of these wrong because you can always check them, right? So let's just practice on this one how you would check it. The way you would check it, you'd say, okay, let's count the carbon atoms on both sides. So how many carbon atoms do I have on this side?
4.
4, right? So I have 4 carbons. How many carbons do I have on that side?
4.
4 as well, right? Then hydrogens, how many hydrogens do I have on this side?
12.
12 hydrogens. How many hydrogens do I have on this side?
12.
12 hydrogens. And then lastly, oxygen, how many oxygens on this side?
10.
10 oxygens on that side. And how many oxygens on this side? So I have 4 from here plus 6 from here for a total of
10.
10 oxygens, right? So notice that the number of atoms on both sides are the same, so the equation's balanced. Does that make sense? You ready to try one? Okay. Let's go ahead and have you try this one. I'll start the poll.
I have a quick question.
Oh, yes. Go ahead.
Yeah, I was wondering, do we always have to?
You know what? Your volume is really low.
Let me check. Do you hear me? Do you hear me now?
Yeah, I can hear you now. Yeah.
I was wondering, do we always have to balance the equation to the lowest multiple?
You typically don't want to have, you know what? Sometimes people will leave the halves in there, but if it's a problem where it's just asking you to balance the equation, go ahead and clear the fractions.
Okay. But in the case of if I, for example, get the double of the balance equation, would it be wrong?
Oh, I see. If you have double, it's not technically wrong, no.
Okay.
But you know, if it's the kind of problem where you know it's multiple choice or something like that, it's always going to be the you know the round numbers, the smallest set of round numbers. Yeah.
Okay. Thank you.
Yeah. Good question. Alexander, did you have a question?
Yeah. How can you show again how you got or figured out that 3 would be the coefficient for the H2O or the 6 or however you did that?
Yeah, because on this step, right at the beginning, I was balancing that because I had 6 hydrogens on this side, right? So in order to balance 6 hydrogens, I had to put a 3 here because 3 times 2 is 6 hydrogens.
Okay.
Okay, 5 more seconds. All right, I'm going to end that and I'm going to share the results. So most of you put B, and in fact, B is the correct answer, right? 2361. So really quickly, what you have here is you have this skeletal equation, right? And you have to balance it. So notice there's no elements here. So this is a little more difficult in terms of to decide what to do first, but you can just play around until you get it, right? But in this case, I can see right away, aha, I have Ca3. So one thing I can start with is to put a 3 there, right? So that gives me 3 CaCl2, right? And then the next thing would be, notice that this is a polyatomic ion, right? So we balance that as a unit, right? So if we have 2 of those, we could put a 2 here, right? And then lastly, we can balance this, right? The Na, 2 times 3 is 6. So that's 6, right? And then the coefficient here is just 1. right? So good job. Most of you got that. Any questions on balancing before we move on? Again, if you didn't watch the video before class, make sure you go back and watch it again after class. You can see some more examples. And let's see, Diana.
I had a question. So I saw on one of the examples we're using fractions. Would it be wrong to leave it as a fraction, or would you always want us to turn it into a whole number?
It's not technically wrong, but you should typically turn it into a whole number.
Okay.
Yeah. Alexander.
Can you redescribe like what the first step would be for balancing a chemical equation again?
Yeah. So you typically want to look for the more complex substances. Well, first you write the skeletal equation, and then you look for the more complicated substances and balance those first. I mean, that's, and then save free elements for last.
Oh, okay.
So, you know, things like O2 or aluminum, those are free elements, right? And the reason we save those for last is because when you balance those, you don't mess up anything else.
That makes sense, yeah.
Make sense? So that's why you save those for last.
Cool. Right.
Jane.
Do you think we could maybe do one more example just to go over the steps again?
Let's see. Do I have another example? Sure, we can do one more example. How about, let's see. Silicon dioxide, solid plus carbon to produce SiC plus CO. Okay, and this is solid, and this is gas. So, okay, so there's your skeletal equation, right? So the first step is so the one thing on this one, right, since you have a pure carbon here, you'll save that for last, right? So you start with either silicon or oxygen. You have one silicon here, so nothing needed there. Two oxygens here, you only have one oxygen there, so you need a 2 here, right? That gives you 2 oxygens. Then everything's balanced now except for that pure element, right? So if you have 2 carbons, you put 2 carbons there. That's kind of the steps you go through.
Okay, thank you.
You're welcome. Sarah.
Okay, so I started hypothetically, I started the Na3PO4 with NaCl. And so I had 2, and then I ended up with 3/2 for the CaCl. And then basing Ca off of 3/2, do you just say like, screw it?
So if you do it that way, let me just cross these out and we can go through the way you did it real quick. Because actually, you know, there's multiple ways to do these. So you started with the Na. So you said I have 3 and then 3.
Yes.
Right? Okay, so you got that. And then the next thing maybe you went on to was Cl.
Oh, I went from Cl and saw that there was 2 on the left side, so I put 2 in front.
Okay.
And then I don't even know. And then I was basing 3/2 CaCl to Ca3/PO42.
Yeah, the problem is if you do that first, then you see the NAs aren't balanced, right? So that's why you would have to go, oh, wait a minute. No, I have to balance the NAs first. So you'd have to change that to a 3 and then go from there.
Okay.
Yeah. Again, sometimes you have to play around with it a little bit. All right, great questions. All right, let's move on, unless there are any more questions, to our stoichiometry problem, okay? So now we want to get back to this question about carbon dioxide, right? This is how much the planet burns, 4 × 10⁵ grams of hydrocarbons, the equivalent of, it's not all C8H18, but we're going to just use this as a representative compound, right? This is how much fossil fuels are burned in total, right? And we're going to use this as a representative compound. It's not all this, but that's okay. It'll give us a close enough number. All right, and the question is how much CO2? So we have the balance equation for the combustion of this compound right here, right? And so we know that for every 2 moles of this, we get 16 moles of CO2. But what do we start with here? We're starting with grams, right? So the important thing to remember is that this is a relationship between moles, not between grams, okay? Between moles of the substance, not between grams of the substance. And you saw in your video, second video you watched today, this example with the pizzas, right? If you have a certain amount of, a chemical reaction is kind of like a recipe, right? And if you have a certain amount of one ingredient, how much of the product can you make, right? So you saw here, right, with this example, that if you have 6 cups of cheese, right? 6 cups of cheese, right? You can get a ratio from the chemical equation, right? 2 cups cheese over 1 pizza, where, let's see that, it's just nothing, where that cancels, right? And it'll tell you that you can, you can make 3 pizzas from that much cheese, right? So it's the same thing in a chemical equation, right? So for example, if I have 22 moles of C8H18, how much carbon dioxide does that produce? Right? So my conversion factor there comes from the chemical equation, right? The chemical equation tells me that I have 2 C8H18 for every 16 CO2. Now, that can be molecules or it can be moles of molecules, right? So I can also write 2 moles C8H18, 16 moles of CO2, right? That ratio holds for either the molecule itself or for a mole of the molecule, right? So then I can say, oh, okay, now I have a conversion factor between these two things, right? So I can start out with 22 moles of C8H18 times, and how should I write this ratio to convert from moles of octane to moles of CO2?
2 moles of C8H18 over 16 moles of CO2.
Let's see, which one, where do I put on the bottom? The moles of C8H18 or the moles of CO2?
The CO2.
Well, if I did that, let me just try that. 16 moles of CO2, 2 moles C8H18. Notice that the units don't cancel, right? So you always got to use your units as a guide in order to write these ratios correctly. So that's not the right way to do it, right? How should we write it?
C8H18 on the bottom.
Yep. 2 moles C8H18 over, and then 16 moles CO2 on top. You see that?
Where did you get 22 moles from?
That's just given, right? If I have 22 moles of C8H18, that's just given in my problem.
Okay.
How much CO2 am I going to get? It's just an example. So then that cancels, right? And I multiply that out and I get 176 moles of CO2. Does that make sense? All right, awesome. Now, let me go ahead. Let's just do a quick poll question, see if you're getting this. So go ahead and try this. Go ahead and try this one yourself. Okay, if you're having trouble, you just start with the 3 moles of CH4 and you calculate each one individually, right? So to calculate the amount of CO2, I would look at the balance equation at see, 1 CH4, 1 CO2, right? So my ratio is just 1 to 1. And I write it so that CH4 is on the bottom and that cancels and I get CO2 on top. So the 3 moles of CH4 produce 3 moles of CO2, right? For the next one, for the moles of H2O, I got to use a different conversion factor, right? You got to get the relationship between CO2 and H2O. Sorry, between CH4 and H2O. Okay, good. Looks like most of you are getting that. Try to finish up in the next 5 seconds. Okay, the right answer is D, right? And most of you got that. So nice work. To do that, you just, again, look at the balance equation. You go, aha, now I have 2 H2O, right, for every 1 CH4, right? So that cancels, and I get 6 moles H2O. Okay, so 3 CO2, 6 H2O. Questions? Does that make sense? Awesome. All right, let's move on. Now, notice, let's go back to our problem that we're trying to solve. Notice we're not starting here with moles, we're starting with grams, right? But we already know how to convert from grams to moles, right? So in other words, in order to solve this problem, it's asking us how much CO2, and actually I want to calculate the amount of CO2 in grams as well, right? Because the amount emitted by volcanoes is measured in grams or kilograms, right? So I want to be able to compare how much is produced from this reaction compared to how much is produced by volcanoes, right? So notice this pattern that we've already seen before for compounds, right? We're going to start with mass. We're going to convert to moles of one thing. Then we're going to use the balance equation to convert to moles of the other thing. And then we're going to convert to mass of that other thing using the molar mass. All right, so we're going to be doing this a lot. Mass to moles to moles to mass. Put that in your brain. We'll be using that pattern over and over. You saw it in the last chapter when we're talking about compounds. And now we see we're going to use the same pattern when we're talking about chemical reactions. Okay, so let's do a couple of examples. Let's start with this one. This is the reaction that occurs, and I don't know why I have 2 arrows here, but it should only be 1. This is a reaction that occurs in an airbag in your car, right? So when you crash in an airbag in your car, there's sodium azide in there, which is NaN3, and when the crash is detected, it is ignited and it undergoes this reaction to form sodium and a bunch of nitrogen gas. So it's all the production of all that gas all at once, right, that fills up the airbag. Okay, so so the question is, how many grams of nitrogen are produced by 6 grams of sodium azide, right? So again, we're going to use this pattern, mass to moles to moles to mass. All right, so we're going to start with 6 grams of NaN3, and we're going to convert that to moles. The molar mass is given here nicely, so 65.02 grams per mole. My grams cancels. Now I have moles of sodium azide, right? Now I want to use the factors in the balance equation to convert from moles of sodium azide to moles of nitrogen, right? So what should this conversion factor be? what should be on top?
3 moles of nitrogen.
Correct. 3 moles of nitrogen to every how many moles of sodium azide?
2.
2 moles.
Correct. Right? You see that? Now that we're at moles, we can use that ratio. Could I have used that ratio for grams?
No.
No, right? Can't use it for grams. That's only between relationships between moles. Okay, so now I have moles of nitrogen. Now I want to convert to grams of nitrogen, so I have to use the molar mass, not of sodium azide, but the molar mass of nitrogen right here, right? So that's 28.01 grams per mole. My moles cancel, right? And I end up with 3.88 grams of nitrogen. Does that make sense? All right, let's do our example for octane, right? So I have, let's see, what did I say? 4 times 10 to the 15, 4.0 times 10 to the 15 grams of C8H18, right? That's the amount of octane burned by the entire planet, okay? First thing I'm going to do is convert that to moles. 1 mole of C8H18 has a molar mass of 114.22 grams. So now I have moles of C8H18. Now I got to go back to my balance equation. And what's the relationship between moles of C8H18 and moles of CO2?
2 to 16.
Yeah, 2 to 16. So how should I write it here? What goes on top?
16 moles. of
16
CO2.
moles of carbon.
16
dioxide.
moles of carbon dioxide, exactly right, for every 2 moles of C8H18. So that's going to cancel. Right now I have moles of carbon dioxide. I still need one more step, right? I need to convert to grams, right? So I'm going to do the molar mass of carbon dioxide. Can you still see what's, yeah, you can still see it. 44.01 grams per mole. And that'll give me grams of carbon dioxide, right? And I end up with 1.2 times 10 to the 16 grams of carbon dioxide. Does that make sense? Again, notice grams to moles to moles to grams, right? Conversion from grams to moles, you're going to be using molar masses, right? Conversion from moles to moles, from here to here, you're going to be using the ratios that come from the chemical equation.
Can we go back to the original question that you just did?
Yeah. So I just want to know how much CO2 from 4 times 10 to the 15 grams of C8H18.
Okay.
Right. This is the amount burned by the world. Okay.
Okay.
You can convert that to kilograms. In kilograms, that would be 1.2 times 10 to the 13 kilograms of CO2. Right. And what we've measured for volcanoes, what geologists has measured from volcanoes is 2 times 10 to the 11 kilograms of CO2 per year. So this is per year from fossil fuel combustion. This is per year from volcanoes. So the ratio, right? The ratio of the amount from volcanoes, 2 times 10 to the 11 kilograms, divided by that due to fossil fuel combustion, 1.2 times 10 to the 13 kilograms, times 100% gives you 1.7%. Right? So volcanoes do emit CO2, no doubt about it, but it's only 1.7% of the amount emitted by the combustion of fossil fuels. Right? So this person who was saying that carbon dioxide emits more than fossil fuel combustion didn't take general chemistry, right? Okay, does that make sense? You ready to try one?
I had a question about one of the steps.
Yeah, go ahead.
So when you get the answer 1.2 times 10 to the 16th grams of CO2,
Yeah.
what did you do in the next line? Because I couldn't really understand.
Oh, you know what? All I did was I converted it to kilograms, and I didn't write it out because I'm running out of room on my paper. But basically, all I did was I did 1.2 times 10 to the 16 grams times 1 kilogram over 10 to the third grams, and that cancels, and I get 1.2 times 10 to the 13 kilograms. Right. So I skipped that, but that's what I did going from here to there. And then this is what volcanoes produce, right? We know that from geologists that report that number. And then we compare the two and we see the ratio. Any other questions? Okay, let's have you try this one. Diana, did you have a question?
Yes, I did. But it's not in reference to this problem. It's
Okay.
one that we already did.
Okay, let's wait until we finish this one first.
Okay.
Okay, try to finish that up in the next few seconds or so. All right, I'm going to end it here. So the majority of you put D, and D is indeed the correct answer. So again, good job. Real quickly, let's just go through how you do that, right? So you're going to start out with what you're given here, 18.0 grams. And you're just going to follow that pattern of grams to moles to moles to grams, right? So you're going to convert that to moles first, right? So you got the molar mass. This is of C6, sorry, let me just start it over. 18.0 grams of C6H12O6, right? Times, now you're gonna use the molar mass, 180.2 grams on the bottom, moles on top, so your grams cancel. Now you have moles, right? So grams to moles. And now you're gonna use the ratio from the balance equation, right? So what's the right ratio here from this equation? What goes on top?
6 moles of CO2.
Correct. 6 moles of CO2 for every 1 mole of C6H12O6, right? So that cancels. Now I got moles of CO2. The last step is to get to grams, right? So moles cancel and I get grams, and I get 26.4 grams of CO2. Oops, sorry about that. Grams to moles to moles to grams, right? Questions, does that make sense? Everybody got that? Most of you did. That's good. Okay, let's see. Diana, you had a question?
Yes. Does it make any difference? So in the problem before, it said that CH4 reacts in an excess of oxygen. Does the excess part, when it has that added, does it matter?
It means that CH4 is the limiting reactant in that. So when it says in excess, it means that CO2 that CH4 is a limiting reactant. So
okay.
We'll talk a little bit more about what that means next time.
Okay.
But it just means that the relationship between the amount of product and the amount of reactant is going to be limited by CH4. Okay, but again, we'll talk about that in detail in our next lecture, okay? Great. Hey, Yoon, do you have a question? Let's see, I don't think I can hear you. Hey, Yoon, if you want, you can type it in the chat because I don't think your microphone's working. Yeah, for some reason I can't hear you. I don't. You're not on mute. So yeah, go ahead and ask your question on the chat. Go ahead. Are there any other questions in the meantime? For the moles of NaN3. Let's see. Oh, so this question says that there's 2 NaN3 for every 3 N2s, right? So if you go back, this ratio, right, is what comes from this balanced equation. Okay, so 2 to 3 here. The number of, when you start out with 6 grams of NaN3, right, you got to convert that to moles. So you go 6 grams times that, and that gives you the number of moles. Okay, I hope that answers your question. If not, just stick around afterwards and I'll look at it and we can discuss that further, okay? So just hang on. Are there any
I'm
other?
sorry.
Oh, did you? I think you got your speaker working, Hey Yan.
Oh, okay. So I'm sorry. Sorry about all that. Because I was just wondering, because I thought that like it's because a 2 is in front of the NaN3. So I thought you were supposed to multiply 3 and 2. So you like in total it would be 6 moles of N3. Or N, yeah.
No, because you start with 6 grams of NaN3, right? And you convert to moles. And then this is the ratio. The ratio is taken directly with the coefficients from the reactions, right? So it's 3N2 divided by 2 NaN3.
Oh, okay.
All right, so you just write it down exactly how it is in the balance equation here, right?
Oh, so if you're doing the balance equation like itself, so that's when you would want to multiply the coefficients so that way they're more equal, just for the balancing equation part.
So don't confuse the stoichiometry with balancing equations, right? So stoichiometry is one thing where you go grams to moles to moles to grams, okay? And then balancing equation is totally different. In order to do stoichiometry, you got to start with a balanced equation. Okay, but don't get them confused. Balancing equations, right? You just go through this procedure that we talked about earlier, right? You write the skeletal equation and you balance blah, blah, blah. Once you have a balanced equation, right, then you can do the stoichiometry part, but they're 2 different calculations.
Oh, okay. And I'm so sorry, I just had one more question.
Sure.
So, so earlier I had a question, but then my speaker wasn't working, so I didn't get a chance to ask.
Yeah.
So it was a part with the balancing equation, how you said like we have to work within the parentheses.
Yeah, when you have a polyatomic ion that you you know your polyatomic ions that you learned for the test.
Yeah.
So when you have a polyatomic ion, you just keep it together. You don't break it up. So for example, here you should recognize this as phosphate, right? PO43 minus. So when you balance that as a unit, right? You don't balance the phosphorus and then the oxygen separately.
Oh, okay.
That makes sense? So you say, oh, I have 2 phosphates here, so I balance it with a 2 here.
Oh, okay. So earlier for the earlier problem, the one with the aluminum and then that one.
Yeah.
And then, so in the parentheses, you don't touch the acetate. So
you balance that as one whole unit. So you have 1 here, 3 there. So that's why initially I'd put a 3 in front of that.
Okay, okay.
Does that make sense?
Yes.
Yeah, so keep those together as a unit.
Okay. And we only keep it like together only for the acetate.
For any polyatomic ion. So remember that table of polyatomic ions? Those are your polyatomic ions, and that's what you want to keep together.
Okay. That's basically it. Thank you.
Okay. Let's see. Alexander, do you have a question?
Yeah. Can you go back to the one you just did, with the information that was given? Or the one that you were just talking about? The one yeah, you just passed. 1 4, I think.
This one?
It was the one, no, the other one where you gave the, that one, yeah. Shouldn't the N2 be 24.02? Or 28.02? Because nitrogen is 14.01.
Yeah, it should be 28.02. Good catch. Yeah.
Okay.
Other questions? Okay. I think what I'll do, since it's 3:18, is I'll end class here, and then I'll stick around, of course, for more questions. But I'll officially end class. So I will stop the recording.